right, so welcome everyone to this new section of Gravitículas. Today speaker is Professor Juan Carlos Helo. Juan Carlos is currently an associate professor at Universidad de La Serena and associate investigator at Instituto Milenio Zafir. So in this talk, he will discuss the experimental sensitivity of the LHC on neutrino mass models through searches on long-lived particles. So, Professor, the screen is all yours.
Thank you. Yes, well, thank you for the invitation. I think this is the second time I give a talk in Gravitículas. I was, the last time I think was in 2020, 2 years ago. This talk is about different neutrino mass models that are connected with the long-lived particles, in the sense that one of the, or some of the particles that they are required to make a mechanism that explain neutrino masses will be long-lived due to the likeness of the neutrino masses. It's based in several papers. I have worked in this direction. Actually, I award a regular Fondesit a few years ago to work in this subject. And well, I have worked with several collaborators, and I would like to thank Martin Hirsch and Giovanna Cotin for sharing with me some of their slides. The main motivation for these research works are the neutrinos, which are they are everywhere, the very sources of neutrinos from cosmic. There are cosmic neutrinos from accelerator, solar neutrinos that are coming from Big Bang, etc. And several experiments they are searching for neutrinos, measuring them, and doing science with neutrinos that are very interesting. And we have learned the last 2 decades a lot of neutrinos. We know that they oscillate. There are 3 types of them. They oscillate each other. They have masses, tiny masses, but they have masses. But there are many things that we don't know also. We don't know if they are ordered in a normal hierarchy or inverted hierarchy, since we only know the square mass of 2 of them due to the measurement of atmospheric neutrino oscillation and solar neutrino oscillation. And we also don't know if they are Majorana or Dirac type. Most of the theories believe that the neutrinos are Majorana. This is mainly because you can build an effective operator at dimension 5 with a standard model fields using 2 Higgs doublets and 2 lepton doublets under the SU2 symmetry. You can build this dimension 5, which is the Weinberg operator. And after the spontaneous symmetry breaking, that gives you a contribution to the neutrino masses. And the question is how you can realize, how you can build this effective operator with the renormalizable terms in the Lagrangian. So you can have a 3-level realization, 3 types of this 3-level realization, which are the 3 different seesaw models, the type 1, type 2, and type 3. Here I'm showing in these diagrams the type 1, which requires having a right-handed neutrinos added to the particle content of the standard model. So in this case, you have this 3-level diagram that will contribute to the neutrino masses. And it's called seesaw because you have heavy particles added to the standard model, which are responsible for the lightness of the neutrino masses. The theoretical expectations of the seesaw type 1 is, so I already mentioned, this is the diagram that they contribute to neutrino masses. So we expect that the neutrino masses are proportional to the Yukawa couplings, square to the Yukawa coupling, and over the new physics scale. This new physics scale, if it's very high, let's say of the order of 10 to 14 or 10 to 15 GeV, then the Yukawas must be order of 1 in order to if we want to fit the neutrino masses. In that case, there's no way to prove this mechanism at any experiment we have so far. But the Yukawa couplings could be much smaller, but we know that from standard model, for example, Yukawa couplings could be of the order of 10 to minus 6, for instance. In that case, the nucleus scale should be around 100 GeV, so we have an extra weak scale CISO. These Rajah neutrinos, they become heavy neutral leptons, which are nearly singlet fermions. From the experimental point of view, a heavy neutral lepton is just simply a heavy fermion singlet with suppressed charge, a neutral current interaction. This is the Lagrangian that we can build, in which the important parameters are the mixing of the H and L with the active neutrinos. There are 3 active neutrinos, so we have 3 types of this mixing with the electron, muons, and taus, and also the mass of the H and L. We know that this mixing must be small from phenomenology. We can fit the neutrino mass data. We have done this in these plots using the Casas-Ibarra parametrization. As seen in these plots, we plot here the mixing square versus the mass of the HNL. This is the lightest of the HNL. Simultaneously, the C tau of the HNL versus the mass as well, for different values of the lightest of the neutrino masses. And as we can see in these plots, for masses of the HNLs below 100 GeV, these HNL are expected to be long-lived particles. So because the C tau are of the order of the meters. This basically what I'm trying to show with these plots. So can the LHC tell us something about the origin of neutrino masses? And the answer is yes, because the LHC can search for these heavy particles, although cannot measure, the main detector at least cannot measure the neutrinos, but they can look for the particles that are involved in the mechanism to explain neutrino masses. So since the heavy neutral electrons are expected to be long-lived particles, there have been several displaced vector proposals. The literature so far displaced leptons, lepton jets, neutrino jets, multi-track displaced vector, vertex, etc. Also, there have been several proposals to build specialized detectors to look for long-lived particles. Here a list, it's not a complete list of some of these proposals. They have different geometry, detector geometry. Here's the phaser detector, Matushla, Codex P, Anubis, Alex modal map. In 2018, together with Martin Hirsch and Simon Wong, we studied the sensitivity of these FAR detectors, which so far the only that is approved is phaser right now, but the others they all want to be approved. We studied the sensitivity of these proposed experiments on the heavy neutral leptons. And as this is one plot taken from one of our paper, we found that we are showing here that these FAR detectors can be sensitive up to masses of 5 GeV for the HNL, and they can reach very small values of the sensitivity on the mixing square, improving the sensitivity of existing current experiments by several orders of magnitude. Also,
Carlos, I'm sorry, can you go back to the previous slide, please? So this B alpha N parameter can be understood as a coupling, a simple coupling between the heavy neutrons, the heavy neutrinos and the active neutrinos, right?
Yeah, it's like the mixing between the mass state, let's say, and the flavor state of the active neutrinos. Yes.
So if it is possible to say something or not? Sorry.
So please, say again, please.
Okay. It is possible just to do a comment. Can you hear me?
Yes.
Hello.
Yes, of course.
Yeah,
yes,
but
please.
Question of Bastian. Bastian, you are talking. Let's say if there is a Yukawa coupling in the Lagrangian, right?
A kind of, yes.
Yeah. So, but the parameter this B alpha n actually contain the Yukawas. You can put everything in front and then recall all of this stuff and complex numbers and so on and call mixing.
Okay.
So let's suppose if you want after that distinguish between different models, you should go, how to say, deconstruct the mixing and found
yes,
all the
yes.
components.
And
Yeah.
you forget about all these components and you you keep only.
Yes.
Okay.
Yes.
Thank you.
So this is how it looks in the Lagrangian.
Yes. Yeah.
Here's the HNL with the current and the neutral charge interactions. And,
Thank you.
and yeah, and if you want to connect this parameter of the model with the neutrino oscillation data, in this case for the type 1 seesaw, this is the relation. So here you have the same mixing, which is related with the light neutrinos and also with the mixing of the neutrino oscillations. So this is for a specific model. So is much more clear now or no?
Yeah, completely.
Okay.
Thanks.
Perfect. Yeah. So the main detectors Atlas can also say something about it. There have been several proposals in the literature. I will discuss what I have done with my collaborators. In 2018, we proposed with Giovanna Cotin and Martin Hirsch an optimized strategy based on an Atlas experimental search that was made for supersymmetry searches of long-lived particles. I mean, it's neutrino search, if I recall well. And we optimized this search for heavy neutral lepton, and the idea is to search for multi-track displaced. It's a multi-track displaced vertex strategy for the Atlas inner detector. And the process that we were studying was the W boson that was produced at the LHC that they decay to a prom lepton and a heavy neutral lepton, that then the heavy neutral lepton decay into leptons and two jets. And we found that the Atlas can be sensitive to HNL masses up to 25 GeV, more or less, and can improve the current existing limits by several orders of magnitude, up to 10 to minus 9 of the value of the mixing square for 3000 inverse femtobar. These plots are taken from this paper that we published in collaboration with Rebecca Beltran, Martin Hirsch, Giovanna Cotin, Arsenio Titov, and Simon Wan, in which we update our previous result from 2018. The sensitivity from far detectors and that I just showed from Atlas can be compared. In this plot, I'm just showing that they are complementary each other. The far detectors can reach masses up to 5 GeV, and the Atlas, for instance, up to 25, but starting at are more or less 5 GeV. So this is nice complementarity between this type of detectors. CMS can also tell something about it. We, together with Giovanna Cotin, Martin Hirsch, and our colleagues from CMS, Christian Peña, Sichi, and Christina Wong, we did a recast of a current search that the CMS did for in the context of CMS Higgs, standard model Higgs decay into long-lived scalars. That was published last year. And this search make use of the CMS muon endcap detector to identify a shower produced by long-lived particles decaying to hadrons, taus, leptons, or photons, and taking advantage of the large CMS still shielding in order to suppress the background. So the idea was that since the LHC so far has searched for heavy neutral lepton, but that are mixed predominantly with electrons or muon, they have not done so far analysis that cover the mixing with the taus. So we thought that that this search could be sensitive to HNL, the mixing with the tau, because it's sensitive to long part decay into taus. So that was basically the idea. This analysis requires a trigger on MET larger than 200 GeV, and the signature relies on a large cluster of cathode strip chambers, the CSC hits in the muon system, the N hits, which is these yellow things for here. Our results, our first results were not very good in the sense that they don't cover new part of the parametric enrichment that has not been covered by previous searches in other experiment, which is in this plot to correspond to the gray area. So we have here a plot of the mixing the HNL in the tau sector versus the mass of the HNL. But after doing this, we propose to optimize this search strategy in two different ways. The first strategy was maintaining the high MET trigger, but with a tiger and hit cuts. So we are optimizing for the HNL, the previous search, CMS search. And the strategy two was lower the cut MET trigger and increase the hit and hits, but using a displaced trigger that will be operative in the CMS for the runtime. In doing this, we found that the sensitivity improves a lot. The black curve corresponds to our strategy one for 6,000 inverse centovar, and the red curve corresponds to our strategy two, which use this new displaced trigger. And in that case, is correspond to our better results, covering new part of the parametric enrichment for the mixing with the tau, and proposing a way to search for HNL, the mixing predominantly with the taus, that has not been done yet at the LHC. So it's a very nice result. And the process that we studied was the same that we studied previously in Atlas, basically. A W boson that decay to an HNL and a prom lepton, and the HNL decay to a lepton and jets. In this project, we didn't study the possibility of, since this was a very new idea, we were thinking also to include, see how we could do, for instance, with mesons that decay, B meson, for instance, decay into HNLs, or even tau leptons, something I will discuss later about taus. Tau leptons decay to HNL for this CMS muon detector. We discussed this with the experimentalists. They think that it was a good idea, but we haven't worked much in this direction yet. In the same line of thought, we were thinking that the other accelerators, such as the BEL2, could be sensitive to HNL that mix with the taus, together with Gilberto Zamora and Claudio Dib and Avi Sofer and Nicolas Neil. Avi Sofer, who is in one postdoc of his. He is an experimentalist. He works at BEL2. With him, we study the sensitivity of BEL2 for H&Ls that mix in the tau sector. So the idea was that the BEL2 will have many taus of the order of 10 to 10 taus, pair of taus, and see how this could be used to set limits or to prove the existence of the H&Ls at this experiment. And so the tau can decay to an H&L and prompt pions, and then the H&L will decay to displaced muons plus missionary. So that was the signature that we studied, and we found that we can set limits that they are 1 or 2 orders of magnitude better than the existing current limits, which is this green line, which correspond to limits from Delphi, if the H&L mass is smaller than the mass of the tau lepton. So this is a requirement that comes from the kinematics of the process. So this is very interesting. We can reach values of 10 to -4, but as already said, the taus are always difficult. So set limits on the H&L mixing with the taus is much more complicated with the case of electron muons. So the limits are not as good. The existing limits are not as good as the limit that exist for electrons and muons. So we could, even though that we can just reach 10 to -4, still we were better than the current existing limits. Okay, so this is what I will say about the neutrinos mass model at 3 level related with the CISO type 1 and connected with long-lived particles. Now I will move to other possible realization of the one-bit operator. This operator can be built at 3 level, as already said, but also at one loop level. For instance, this one diagram. But there are several possibilities in this paper by Toshihiko Ota, Bonnet, Winter, and Martin Hirsch. In 2012, they studied systematically all the possibilities that to build one loop neutrino mass diagrams. And this year, together with Carolina Arbeales, Martin Hirsch, Cristian Cepedello, and Sergei Kovalenko, we continue basically this work and study like all possible phenomenological allowable models for neutrinos at one loop. And we found that actually the name of this paper is how many one loop models are there, something like that. It was with a question, and we answered that question. We found that there are 2 types of models, that neutrino mass model at one loop. Basically, we can divide it into 2 types, roughly speaking. But there are several possibilities. We studied all of them. One type is neutrinos that have dark matter candidate, and the others that doesn't have or don't have a dark matter candidates. Here I have 2 examples of these 2 types. One is the scotogenic model, which is a very famous model, was proposed by Ernest Ma in 2006. The idea is just construct one of the simplest possible one-loop model. Here's the diagram. You have a right-handed neutrino and an additional scalar, which is doublet under SH2 symmetry with a hypercharge 1/2. So you can build this diagram, but the problem of build this diagram is that since you have the right-handed neutrino, you can also build this other diagram. This is type 1, because if you have the right-handed neutrino, the right-handed neutrino will couple to the Higgs and the lepton, and you will also build a 3-level diagram. So the expectation of this is that the 3-level diagram will dominate in comparison with the one loop. This one will be a subdominant contribution. But in order to avoid this 3-level contribution that we expect that could be larger, it's not always the case, of course, but for most part of barometric aberration will be like that. An additional symmetry is added to the standard model as C2. So with this C2, you forbid the three-level diagram because this right-handed neutrino is odd under the SU2, so under the C2, and the Higgs and the lepton are even. So the term in the Lagrangian is not singlet, let's say, at the end under the representation of the C2, so it's forbidden. Okay. But you can still build this loop diagram because this L is even, the N is odd, and the is eta 0 is odd. So this term is allowed, you can have it because it's a singlet under this symmetry representation. As a consequence of this, one of your particles in the model, the lightest one, will be stable. So additionally, you have two dark matter candidates, the neutral particles in the model, which come from this neutral fermion and from this doublet scalar. So it's very nice model, very economic model, and can explain neutron masses and at the same time have dark matter candidates. But what if
Juan, sorry, a part of this this scotogenic model gives you these dark matter candidates. In what advantages do you get from this model in comparison with the simplest CISO type 1 model in the neutrino phenomenology, let's say? Keeping apart the dark matter things, is there something more interesting?
Yeah. This is what I wanted to talk now. That there are a few features, phenological features that are interesting from avoiding. I mean, just dropping this requirement of having additional symmetry, this C2 symmetry. If you drop that, then you still need to avoid the three-level contribution, right? So you still have the same problem, but you can avoid that just with the particle content of the model. So you need to go to higher representation of the particles in the loop, in which you won't have particles that will make naturally a three-level contribution like their right-hand neutrinos, and then you can still avoid the CISO contribution. And for some specific, not all of the particles in the loop will give you allowable models, but the phenological allowable models. But this is one example that you can build, and you can still explain neutrino masses without this requirement. And the consequences of doing that is, well, first, you don't have a dark matter candidate in this case, but you will have particles with multi-charge particles. In this case, this, for instance, this S1C3 means that the 1 is singlet under SU3, the 3 is triplet under SU2, and the other 3 is the hypercharge value. So this one is a triplet. You have a 4-charge scalar, triple charge scalar, and double charge scalar. And the fermion here, it has a triplet, triple charge fermion and double charge fermion. So for this specific model, you can build other models. This model is taken from this paper that we wrote with Carolina Reales, Giovanna Cotin, and Martin Hirsch in 2020. So when you study the phenomenology of this at the LHC, you found, this is what we found, that we saw that this was interesting. That for instance, since here we have this 4-charge scalar, which now here I have the name is H, this 4-charge scalar can decay to 4 leptons on one side or to 2 Ws and 2 leptons. So this is the two possibilities that this 4-charge scalar can decay, because it will decay, okay? It will decay to the standard model particles. So first of all, we have that all these particles will decay to standard model particles with at least 2 same sign leptons. So this is one of the conclusions. And if you search this at the LHC, you can search it just by per production. You can per produce them, and you might have a signature like with 8 leptons or 4 leptons and 4 Ws, or even a lepton number violating signature, which is if for in one branch you decay to 4 leptons and in the other you decay to 2 leptons and 2 Ws, which will be 6 lepton and 2 W, which violate lepton number by 2. So in our model, the multi-lepton events have larger rates than the dilepton events. You also can have dileptons, but these are the dominant possible production modes. And also these multi-charge scalars, they will be naturally long-lived. So this is like the consequence of dropping the C2 symmetry, forgetting about the possibility of having dark matter candidate, which of course is very nice. But if you do that and you don't impose an additional discrete symmetry, then naturally your model will have multi-charge particles that will decay to, for instance, in this specific case, to multi-leptons, and they, for most part of the parametric or a large part of the parametric region of your model that fit neutrino masses, which is what I have here, your particles will be long-lived. So this is our conclusion, which we think is interesting from the phenomenological point of view. I don't know if that answers your question.
Yes, yeah, yeah, but it was before entering into this idea, the new idea that it sounds pretty much interesting. It was just a comparison between the scotogenic model, which is very well known and famous, with the type 1 seesaw in the neutrino. For instance,
with the type 1.
Type 1, yeah. But for instance, this scotogenic case has also long-lived particles, or not?
The scotogenic in this model, no, you don't. You have dark matter candidate because the particle will be stable.
But I mean, you can, in my understanding, you can select the scalar from the doublet as the dark matter particle, and in that case, N will be unstable. And I'm wondering if this N right-handed neutrino can be long-lived in that case.
I'm not sure. Maybe it could be that the could be, but I don't know. I don't know if in that case the parameters that fit the neutrino masses and also explain dark matter, it gives you at the end that this N for the specific choice that you were saying needs to be, it will be long-lived. I don't know.
I have a question. Dark matter can be stable or not? A WIMP, let's say.
In my opinion, it must be stable.
I mean, in my opinion, depends, right? Or maybe, because if dark matter is stable, yeah, we are lost. Basically, there is no decay, so we cannot see, I mean, in an experiment, right? Because we are not going to see the final state of the decay. Yeah, assuming that the final state are particles in the standard model. But my question is pointing to the, I don't know, to this stuff, I don't know, with the origin of the universe or the evolution of the universe. What happens if dark matter is stable? There is any consequence?
Maybe you are, well, Juan Carlos.
Please. No, please go ahead. You are the expert in dark matter.
No, if I am I understand your question. In most of the models, when you introduce this WIMP particle is stable. For instance, in this scotogenic, you can choose N, either N or the neutral component belonging to this eta 0, this inner doublet scalar. And of course, at what you say is correct at the collider level, that when you produce them, you cannot see its products in terms of standard model particles, because you only miss, you have missing energy. But normally in this type of models, from the particle physics point of view, you require, this is the typical requirement on dark matter candidates, that the particle must be stable on cosmological scales.
And
yeah, al neutral.
In particular, in this, as I've said, in this scotogenic, you must choose one of them between the neutral component of this eta 0 or the right-handed neutrino.
But at least must be stable for let's say, for the age of the universe, right?
Yeah.
So with that, we can put let's say a low limit.
Yes, in half-life.
Yeah, exactly. Half-life of the age of the universe. Yeah.
Yeah, normally.
Yeah. So, but in principle, there is no any theoretical, how to say, sentence or I don't know, or theorema or something like that to say that must be stable, right?
Completely or absolutely stable. In my understanding, it's not a necessary requirement.
Yeah, it's not a must, let's say.
It can decay in principle, but with a half-life very, very long, more about 10 to the 25 seconds, something like that.
But this is something like the age of the universe, right?
Much more, in my understanding, but it depends on the model. Well, I'm not an expert in that. There is a lot of models in that sense.
Okay.
Yeah, but it's interesting.
Thank you.
Okay. Okay, thanks for the discussion. So I was mentioning that you can have these particles on this model will be naturally long-lived as a consequence of the smallness of the observed neutrino masses, together with the high multiplicity of the final state. So these two things lead to long-lived multi-charge particles. So since we will have now multi-charge particles, they will decay to several other particles. So you have a multiplicity that they reduce the total decay width, and the parameters here, the couplings, the masses, they enter in the neutrino mass diagram. So they will have some, they can have some, not all possible values, but you need to fit the neutrino mass data. And we did that, and we found that for most of the parametric region, or a large part, especially when this multi-charge scalar is the lightest of the particles in the model, you might have a long-lived multi-charge particles. So this is plot is the C tau versus the lambda 5, which is this coupling for this for charge scalar, and this dark area correspond to C taus, which are larger than 1 millimeter. So basically, the idea is to show that these curves are the values that we need to fit the neutrino masses for different values of the masses of the particle in the model. And most of in this case that we choose, most of the parameters leads you to have a C tau very large. This is very interesting. The current limits, there are non-existing searches so far that cover exactly the multi-lepton signal that we have just proposed, which is this one multi-lepton signal, because we have a lot of leptons. But many of the current searches can set limits on this on our model. Stable multi-charge particle searches, displaced vertices, disappearing track, prompt searches as well, but will depend on the parameters for model. So we haven't studied in much detail an optimized search that might be done for this model at the LHC. This is something that we would like to do in the future. I also would like to mention that there are other possible models that we can build at one loop, which will lead to different signatures. For instance, we can have more particles here, which has color. This 3, it means that this triplet under SU3, so these two scalar in the fermion, they have color. So in that case, you can reproduce them through gluons. And in this specific case, they will decay also to leptons and jets and W's. Okay, so there are other possible, but with the same conclusion that for a large part of the parametric region that explain neutrino masses, we expect the multi-charge particles to be long-lived. Okay, so finally, I will comment on other possible realization, not for the one-meter operator, but for a higher dimension effective operator. So the one-meter operator is dimension 5, but we can, if we add 2 Higgses, 1 Higgs and Higgs dagger, we can have a dimension 7 effective operator that also after spontaneous symmetry breaking will lead to neutrino masses, or dimension 9, dimension 11, etc. Right? And we study this as you can open, let's say, this dimension 5 one-bit operator, and you find you have 3 level realizations, which are the seesaw. You can do the same with dimension 7, and you find that there's only one diagram, which is was studied in these papers, one diagram that gives you neutrino masses, and at the same time is what we call genuine in the sense that the naturally is the leading order contribution. So there is no 3 level seesaw diagrams for this model. And also for the dimension 9, the same thing. We found that in this paper with Ana Miati, Oscar Castillo, Renato Fonseca, and Martin Hirsch in 2018, we found there are only 2 diagrams that they has this feature that they are genuine in the sense that they does not appear dimension 7 or dimension 5 or one loop dimension 5 contribution that one expected might be could be of the high. Then in that case, this diagram will be subdominant contributions. So, but there are other possible models. The complete list is in this web page of Renato Fonseca. And we study with Carolina Reales and Martin Hirsch. We study, and sorry, I don't remember the rest of the people that we study this. Okay, with Carolina Reales and Martin Hirsch, we study if in these cases, in this model, for instance, this dimension 7 level realization of neutrino masses, we can have long-lived particles, and we found that it is possible that since this fermion, which is a triplet under SO2, so we have 3 fermions, doubly charged, singly charged, and neutral. The total decay width is correlated with the overall neutrino mass scale. So since there is no lower limit on the lightest of the neutrino masses, if you start to decrease of the value of the lightest of the neutrino masses, you can increase the total decay width of the neutral fermion in order to have a long-lived particle. But for the singlet charge and the doublet charge, it's different because they will decay to a pion and a W. And in that case, the parameters that are involved in this process, they are not related with the neutrino masses, so there is an upper bound on the C tau. And for the case of the scalar, this scalar, which is a quadruplet under C2, it can decay on one branch to 1 W and 2 leptons, and the other at 3 W. These are two possible decay modes of this scalar, because can decay in this direction, and the Higgs will be mixed with the W's. And in this other direction, here there's the leptons in the diagram. So it could be a W and 2 leptons. And there is only for a tiny part of the parametric region, you can have a long-lived scalar. And it's just the same part of the parametric region that you require in order to have a lepton number violating signal, because it's just the value that in which these two decay modes are of the same order. So is in that when this scalar is long-lived, it will be the best possible choice of the parameters that explain neutrino masses, and also that in the sense that the decay this scalar prefer to decay equally to the 3 W's and 1 W and 2 leptons. So we expect that one of the signals will be 4 W's and 2 leptons, two same sign leptons, which is a lepton number violating signal, which is very important. If we find this, we will prove that the lepton number is violated, and also that the neutrino are Majorana according to the black box theory. And this is for dimension 7. For dimension 9, we studied the same. We found similar conclusions. This is the fermions from this quintuplet. No, sorry. This is in this model we have a fermion which is triplet, quadruplet, and quintuplet under the SO2 symmetry. So, and we found that in all the cases the neutral fermion can be long-lived if we choose the lattice of the neutrino masses to be of the order 10 to minus 6 electron. Okay, so finally the conclusions. So far, no definite sign of new physics at the LHC has been found. Many new experiment proposals for long particle searches exist. Heavy neutral leptons from neutrino mass model are expected to be long-lived. We studied the LHC discovery potential for long-lived H&L at main detectors, the CMS Moon system, and also Atlas inner detector. If the H&L exists, they might be discovered through long-lived particle searches at the LHC. We also discussed one-loop neutrino mass model, which does not require additional symmetries to be the leading contribution to neutrino masses. We show that in this approach, multi-charged particles, which are long-lived, naturally appears as a consequence of the smallness of neutrino masses and high multiplicity of the final states. Different searches can be sensitive to this type of models, from searches of stable multi-charged particles to displaced vertex searches. Multi-lepton signals can arise in our models. And we also study the possibility to explain neutrino masses through 3-level realization of higher dimension operator, and we found that in that case, the fermions that appears additionally to the particles standard model, the new fermions can be long-lived if the lattice of the neutrino masses is very small, around 10 to minus 6 electron volt, and for the scalar of these models, only for a small part of the parametric region, which is the same part that we require in order to optimize the possibility to find lepton number violation with this model, within this model. In that case, you can have a long-lived scalars with this particular model, which are 3-level realization of higher dimension operators, effective operator. Thank you.
Thank you very much, Professor. It was a really interesting talk. Does anybody have a question?
I do.
Go ahead.
Once again, yeah, very nice presentation, Juan Carlos. I have many questions, most of them very naive. For instance, if you have, my first question is, you have about the backgrounds that you have from the standard model. For instance, do you expect something like something in the standard model that behaves like a long-lived particle and mimics the signals that you are looking for?
Well, it's a good question. For instance, well, can be answered at different levels. In this Atlas, in this search that we propose, as you can see here, our limits start at 5 GeV, right? So the reason of that is that we impose one of the requirements of this search, which is what based in this Atlas experimental search. In this search that the Atlas made for supersymmetry, searching for supersymmetry with a parity violation, they claim to have they claim to have zero background. Okay, and in order to have zero background, they set some cuts. And one of the cuts is that the invariant mass of the products of the decay need to be larger than 5 GeV. And the reason of that is that you are trying to avoid mesons that leave some distance, B mesons or things like that. So you have in the standard model, you have mesons that they will leave and might be a source of background. So that's one of the reasons that you have this cut. On top of that, you have instrumental background, which is very difficult to take into account. For instance, that's why in order to work on this, you need to. I mean, if there are different levels, and that you can do this kind of estimation for the far detector, which is say zero background, because that's what those detectors are specialized for long-lived particles. That's what they say. They trying to sell you that they will have zero background. But if you want to study, for instance, for CMS, it's not the case. And there are sources, maybe not from the standard model, because here you are in the muon part of the detector, but still this is very technical to know what are the sources of the background. So that's why we have worked with experimentalists in order to make our prediction in the best possible way. In this case of the Bell limits that we work with Gilberto, we draw two curves. One of them assumes zero background, and the other is with 875, which is a number after some assumption that the Avi software did. I mean, with the assumption that he knew about the detector itself. So it's a good question. It's not easy to answer that question because it's very technical. Yeah.
Could I provide a comment? Because Atlas and CMS were designed for jet measurements. They have both have very bad particle identification. So in your search, it's better to use LHCb or Bell and so on detectors with very good particle identification.
Thank you.
No, but it clarifies my question very, very much. Thank you.
So I have a question about your. Can you show the slide? I don't remember the number, but it was what? Maybe the last one.
There are no numbers.
Yeah, no numbers. So yeah, okay.
I know 24, the last one.
Okay, could you? Maybe when you have the cut before 5 GeV in mass. Related to the question of Bastian, actually.
This one.
This one. Yeah, exactly. So, okay. So, but the situation is the decay length, let's say, right?
Mm.
So, okay. So, but the decay length basically depend on the decay width, right? So,
Yes.
but the decay width is proportional to the mixing and the mass of the particle with some other factor. So, but let's suppose that you have a particle with mass equal 3 GeV, but the mixing is low. So the decay width or the length, the half-life or whatever, depend on this. So basically you can tune the parameter of the mixing in order to do the particle live or travel bigger distances, right? So in this case, anyway, you are not going to have background because particle is going to decay very far.
Yes.
So let's suppose that I choose mass 3 and a proper mixing in order to do the particle decay in a place different to the meson's decay. Why you also put a limit in 5 GeV? It is excluded, that possibility. That is my question.
Because 5 GeV is related with the mesons. I mean, it's standard model particles, which for instance, the B meson has masses around 5 GeV. Let's say it's try to avoid background coming from meson decays.
Yeah, okay, but look, let's suppose mesons, let's say B meson, around 6 GeV, right?
But
decay.
Because of the, because of, yes.
Yeah, okay, decay. You have the background from mesons. So let's suppose now you have a heavy neutrino with mass 4 GeV. Assuming that the decay width is similar to mesons, for sure you are going to have a huge background, right? Because are going to decay in the same place in the detector, same region, right? But if the decay width of the neutrino is different, let's say mixing is smaller, that decay is going to cross the region of the detector where mesons decay. And you are going to have a longer, let's say, displaced vertex. So, but mass still is 3 GeV. You change the mixing. So that is why I do not understand why you cannot go.
I understand your question, but in this particular case, we base this strategy on this previous Atlas search, and they claim that if you search in Atlas inner detector, basically is between 4 millimeters and 300 millimeters, and they tell you that you have to have the invariant mass of your particle must to be larger than 5 eV. That's what they use, let's say. And in that part, with that cuts, in that part of the detector, they say that they have zero background. Yeah, it's true what you said, that maybe you can play with that and relax the cuts that they use. But then you enter in a different territory in which that might, I mean, because there are a lot of technical issues here. So it's true what you say. Maybe you can relax that cut, but then your result won't be so reliable, let's say, because as Sergei just said, there are a lot of issues. I mean, experimental issues that they're not so simple.
As I understand, first of all, let's say standard procedure of Atlas requires momentum more than 5 GeV for any particle.
Okay.
So it's
okay. So it's not a problem for heavy neutrinos. Okay, I understand. Okay.
And another one, but there are few groups which are trying to work with, let's say, special features of tracker, trying to use tracker only, not colorimeters, not Muon system, but tracker only, and try to go to low momentums. If somebody interested to do such search, this person has to communicate with this group.
With the tracker guys.
Yeah, with
okay.
Yeah, Sorry, I didn't hear well everything, but yeah, I mean, you don't have a threshold of 5 GeV. So in certain characteristics, yes, but you can also have a threshold of like less than 1 GeV. There are many groups that are working on that right now. And if you're using the inner detector, you're gonna have a better precision, like resolution, than using the other part of Atlas. But as like Sergey was saying, of course, the best way to look for this will be in something like LHCb. The only issue with LHCb is that it's a forward detector. So if you want to check the whole region that you might have an event, then CMS and Atlas are better. And CMS is even better than Atlas because it has a higher magnetic field.
Okay, thank you. Thank you very much, guys.
Okay, so everyone else, guys, if there is no more question, then thank you again, Professor, for the nice talk.
Thank you.
And
Thank you, Juan Carlos.
I will see you all, hopefully, next week in the last talk, if I am not mistaken. So thank you, everyone. Bye.
Bye. Ciao, ciao.
Thank you.
Bye. Thank you,
Bye.
everyone. Thank you.
Ciao, ciao.
Ciao.
Ciao.